Okay. So I'm Deron. I think I know everyone at this point, but I came onto this project a year and a half ago, and we just finished up with the initial grant phase back in September, turned in our final report to KDOG. So I'm just going to give a little bit of an overview of what we did during the initial grant and our findings from it. So methane is a potent greenhouse gas with an 84 times global warming potential compared to CO2 on a 20-year basis. The BIL put money away to give to the Department of the Interior, which the Department of the Interior then gave to state oil and gas departments to plug orphaned oil and gas wells. So chain of money goes BIL, Department of the Interior, KDOG, KGS. KDOG plugged 635 wells with the initial grant money, and they have submitted another 18 from plugging. We finished the initial grant in September, like I said, and now we're starting phase 1 measurements. So when I first came on, we were working with the Well Done Foundation, and we had them around for about 50 measurements to help us get our feet on the ground. We're using a different setup now for measuring methane from orphaned oil and gas wells. So this is a static chamber setup. Our static chamber is made out of Schedule 80 PVC pipe. It's heavy. It's not as heavy as the old chamber was that we were using. It's a fixed volume. We monitor the concentration of methane within the chamber once we put it over a well, and from that we can get a flow rate. We only use this for low flowing wells because obviously methane is an explosive gas, and there's other explosive gases that come out of these wells, and you can't build up too high of concentrations or else it's a dangerous situation. And it's also just that there's a little bit of size constraint as to what the chamber can fit over. So the other method that we use is using the high flow 2 sampler from Simtech. This is a fan system that draws in air at a fixed rate. It's coupled with a portable methane analyzer. So the fan draws in air at, say, 10 square feet a minute. The methane analyzer knows the concentration of methane within that air that's moving through, and from that you get a flow rate. We normally put a tarp over top of the well just to keep wind from dispersing any of the methane that's coming out of it. Both of these tests run for about an hour. The individual measurements for the high flow are about 10 minutes, so cumulatively an hour, and we take a break in between measurements. For the static chamber, it depends on the rate of flow from the well. Sometimes it's 5 minutes, sometimes it's 10, but it's always cumulatively an hour, just to keep some consistency in between everything. So currently, we've measured 127 orphaned wells across 28 counties. Owsley County is not included on there because we were there earlier this week where we picked up an extra 2 wells. And they are not part of the pie chart shown here because I haven't pulled the data from there yet. But the pie charts are showing the total quantified methane on a grams per hour basis. So that's the 3,660 grams an hour of methane. Pie chart on the left is showing total breakdown by type. So 67% of that 3,660 is coming from gas wells. Pie chart on the right is showing same breakdown color-wise, but each slice is an individual measurement. So one well makes up 24% of our total measured emissions, and that well is a gas well. So as you can see from the rapidly decreasing size of the individual measurement slices, the minority of wells make up the majority of methane emissions. And gas wells tend to be our highest emitters. So to drive that home home a little bit, here's that same representation, but on a bar chart with a logarithmic scale. Median, mean. You can see this is a very right skewed data set. Our mean value is 30.7. Our median value is 0.4 grams an hour. Big departure between the mean and the median. And despite precedent set forth by EPA, we did not feel like it was appropriate to use the mean when considering what the total population was doing. So one of our deliverables to the state was to give an estimation of methane abated through the plugging of the 635 wells part of the initial grant package. Even though traditionally the EPA has used the mean, this is a right skewed data set. We did not think that was appropriate. So the question came about of how do we estimate a range of abated emissions from the plugging of these wells? Because we didn't measure every well, and for reasons I'll talk about later, even if we did measure every well, these are still just estimations. So we turned to bootstrapping to come up to a good estimate of potential abated emissions. So to give a little bit of a rundown on how bootstrapping works, I'm going to walk you through the polka dot chart and hopefully not lose anyone along the way. So have your imaginary total population. Hardly anyone gets to sample a total population of anything. So you have your sample set. And what bootstrapping does is it randomly pulls stuff from your sample set and recalculates statistical values with the values it pulls from your original set. So this sample set would be 30.7 mean grams an hour. Each of the bootstrapping resamples will have its own unique mean that is built from values within the sample set. And so when you do that, a good visualization for it is to have a histogram where the columns are bins representing where the mean for the resampled calculated bootstraps fall into. So looking at this, you can still see the influence of that right skewed data set. Most of the time, the new calculated means will fall below the actual mean of the data set. But what we gathered from this is that we have a 95 confidence interval of 11 to 55 grams an hour. This is a wide range, but our data set is wide, so it was to be expected. And then when you apply this out to the 635 wells plugged in the initial grant package, it comes to an estimate of 61.2 to 305.9 tons a year of methane abated through the plugging of these wells. The state, when we gave this to them at first, were a little bit hesitant about how to use this number because they were looking to fill in an Excel sheet that DOI had given them. But using an average value or even using the median value, we didn't feel like was appropriate. So this is the solution we came up to. The other reason it's good to give an estimate, in my opinion, is because these things are very dynamic systems. So this is an oil well located in Lee County. Even though pictures aren't from the same angle, you can tell that in October of 2022, there wasn't at least as much oil staining at the surface as there was by the time we got onto it in May of 2024. So something happened in that year and a half that changed the way this well functions at the surface. We don't know what it was. So these things can be very dynamic across months and years, or hours and days. So this is a well we measured in Menifee County, and I'm going to try to bring up the graph so that people can see it. Maybe not. There we go. So like I said earlier, we run 6 10-minute tests. Everyone can see this big jump up that happened during a test. But what is also interesting is if you remove this big jump, which makes reading this impossible, you can see that there is actually a slight buildup happening until that huge jump up occurred. So we just happened to be there for the hour where this happened. It could do this 5 times a day, could do this on the hour every hour. We don't know what it does. All we know is what it was doing during that hour we were there observing it. So how do you calculate an emission value for that well when it displays such erratic behavior while you're observing it? Which is just another reason why we did what we did in estimating a value. So then just one more example. This is an injection well in Hancock County that we had set up and we were actively measuring when this started happening. So that's brine coming up through the well bore. It was an injection well. We don't know of any active production nearby. We don't know how often it does this either. There was some salt crust around the base of the well, so it must do it semi-regularly for that to build up over time. But clearly dynamic systems that have forces behind them that we don't completely understand. One way we're trying to understand this, though, is by splitting up into subtypes. As of now, our subtypes are still pretty right skewed. It's basically the same problem we have with the bigger population. And some of them we just don't have enough samples from yet to get any accurate measurement or to get any accurate statistics from. You can't take 2 wells and say this is an average value. And then it also seems like surface infrastructure may be playing a role. So we decided to start assigning type 1, type 2, and type 3 wells. The basic principle behind this is a type 1 well has all of its valves exposed and is not interacting with the atmosphere as much as a type 3 well would be, which is completely open to the atmosphere. Type 2 wells are wells which we had a hard time fitting into the other 2 categories. That well has its rod sticking up 30 feet. So I don't know, or has its tubing sticking up 30 feet. So it's hard to tell what's happening on top of that without getting a ladder. And this is just another well that's in Breathitt County. During the 22 floods, it would have been underwater by 10 or 15 feet. If you convert its methane emissions to a CO2 equivalent, 319 metric tons a year, roughly equal to the emissions of 70 cars on the road on a yearly basis. So as we measure more wells through phase 1, we'll hopefully arrive to some better estimates. We'll see that 95% confidence interval start to close, hopefully. And we're going to continue exploring possible drivers of emission rates to work towards this scheme that Marty will talk about a little bit, and that Stacy Woods will be talking about in 2 weeks about prioritizing wells for plugging. So with that, I'll hand it over to Marty and let him talk about some chemistry behind the gas.
Thanks, Deron. Mouse working? So the mouse work, Deron?
Yes.
There it is. Okay, got it. Sure. Screen share here, so I can stop share.
No.
Oh, there it goes. Got it.
Is it still sharing?
Yep. Should be. Very good, thanks. Okay, so I'm just going to follow up with some of Deron's discussion and narrative about the emissions, and with some comments about the gas chemistry and what we see. So in addition to being interested in methane emissions, we're also interested in whether other types of gases are being emitted from the well. And basically, at the end of the day, what we see are the principal gases that we've sampled so far consist primarily of nitrogen, oxygen, and methane. The higher molecular weight hydrocarbons, ethane through butane, that's the C2 through C4 that you see up there, are basically trace amounts up to about just shy of 12 mole%. And then the other, what we call fixed gases or non-hydrocarbon gases, include CO2, carbon monoxide, and hydrogen, and they're typically less than 1 mole%. So this bivariate plot's got a lot going on it, and there's a lot of information here. So I'd like to unpack it a little bit. So on the y-axis, we have concentration of methane in mole%, right? And then on the x-axis is the concentration of nitrogen plus oxygen. And just as a note, when we look at the nitrogen-oxygen ratios from the samples that we collect, those averages are right about those ratios are about 3.76. And so by comparison, if you took an average atmospheric sample, the ratio of nitrogen to oxygen would be at just right at 3.71. So we have just slight excess of nitrogen compared to atmospheric, and we can see why that's the case. So I hate multitasking in this microphone is feeding my bandwidth here, so I'll just hold on to this point. Okay. So again, concentration of nitrogen, oxygen, concentration of methane, and what I want to bring to your attention here is it turns out that over the last couple of decades, we've been very deliberate about collecting reservoir gases at depth when we have an opportunity, and also as part of our projects. And so that actually ends up being very beneficial for our purposes here, because we have a reference point for a potential reservoir of gas that would contribute to the wellbore rate. So here, these bars right here show the concentrations and the ranges of methane for what we call natural gas and then oil-associated gas. So oil-associated gas is basically gas that's dissolved in the oil, and it basically is dissolved as oil is being produced from the reservoir. Natural gas is from a true gas well. This is the range of values we typically see for methane in our subsurface reservoir gases. And these gases include everything from probably Cambrian all the way through Pennsylvania age reservoirs. On the other hand, shown down here in the lower left plot is my variant plot. So you can see the range of nitrogen plus oxygen values. So typically, you sample a subsurface gas and you got oxygen in it, that's a red flag because you don't find oxygen in the subsurface. That means that you contaminated your sample. So really what you're looking at here, these are just nitrogen concentrations. So typically we're less than 10% nitrogen in almost all of our reservoirs. Actually, it's usually less than 5, okay? So you can see that nitrogen really constitutes a small proportion of our subsurface reservoir gases. So what I plotted here is, as Deron mentioned, these different types of wells we look at, oil versus gas versus injection. These are the nitrogen-oxygen ratios versus methane for oil wells, which are shown with the green circles, and gas wells shown with the red circles. And moreover, what I've included is the different emission rates for each of these types of wells. I show oil wells that produce less than a gram per hour. That's the little small circles. Ditto for the gas wells, right? And then for wells that produce more emissions on an hourly basis, more than 10 grams per hour, those are the largest circles. Again, green for the oil, red for the gas. Okay. So the first thing I want to point out to you is that you can see there's a really nice inverse correlation between methane versus the nitrogen oxygen, right? Really strong correlation there. What that suggests then is that basically what we sampled right at the surface or just inside the wellbore is basically a binary mixing system from a geochemistry perspective, right? So we have two reservoirs contributing to the gas, the atmospheric reservoir, but then the subsurface reservoir right here. Okay, so basically we're looking at a mixing trend between these two reservoirs. The other thing I'm interested in is as we sample these wells, does the emission rate, i.e. how strongly that gas is being pushed out of the wellbore affect the composition of the gas, okay? And it turns out to be a bit of a messy picture. So if we look straight at the gas wells, what we do see is that in general, a higher getting gas well, i.e. those with the large red circles, tend to plot up big concentrations with higher methane. Conversely, the slower emitting gas wells, which are kind of down here along the abscissa, they tend to have lower methane concentrations. The oil wells tend to be a messier picture and a little bit harder to understand, and I will have to say that I don't fully understand them at this point. Other than to say that as we collect gas samples in the field, Deron didn't get into this because he really kind of looked at the measurements that we've done, but we looked at the Well Done Foundation. They also used a very large chamber to do their measurements. And what happens is over the course of say 12 to 24 hours when they're collecting this gas in this large chamber, you can imagine that a low emitting well, in which gas may be only moving into the chamber via diffusional process, will never fully displace the atmospheric gas of that chamber. So what Well Done would do at the end of their test, they would come pull a gas sample and then send that off to the lab for analysis. What I think has happened, in fact, you're thinking ahead, you're thinking analytically, you should be saying, Marty, you should plot this, do the same plot, show the different measurement techniques, right? To see if there is a measurement effect on the gas concentration. And so that is indeed something to do. But what I suspect is that a lot of this noise down here is the fact that, especially in the early days of the project, we were pulling gas samples out of a chamber that had not been fully evacuated, was still full of atmospheric gas. That ends up diluting, of course, the methane concentration. So that's one of the challenges we have, or we need to look into further. It's an interesting thing, especially for low emitting wells. When you're in the field, I tend to use the word estimate when we're discussing these types of measurements for reasons Deron brought out. By the end of the day, we have to be very careful not to get too far over the tips of our skis in terms of our confidence about in terms of these measurements. So we tend to use the word estimate when talking about these measurements.
Yeah, go right ahead.
So the bottom, you show the oxygen.
Yep.
What about the carbon dioxide?
So CO2 tends to be pretty small, less than 1 mole%.
So even in the gas body, the reservoir, CO2 something.
In general, that tends to be the case, yeah. We typically don't. There are some reservoirs in eastern Kentucky that have higher CO2, so they might go up to say 15 mole%. St. Peter sandstone, but we haven't gotten into those yet.
The gas wells, pretty much high, like, say 90% of the natural gas.
Say again?
For the gas wells,
Uh-huh.
the gas come out maybe over 90% is the methane.
Yeah, the gas wells tend to definitely have higher methane concentrations, and that goes back to this concept of what we call wellbore openness. So what happens when operators in the field on an oil well, this is what we have observed, is that if the oil well is sub-economic, so they're not making money, but they got a pump jack going on the well, they got a motor going on the well, rods and tubing, and they got a well next door that they think they can take money off of, they're not gonna go buy a new pump jack and a motor. Guess what they're gonna do? They're gonna strip all that off of the sub-economic well, right? Put it over onto the other well in hopes that they can make money. Where does that leave the sub-economic well? Leaves it open to the atmosphere. Gas wells mechanically are simpler systems. Basically just a series of flow valves coming into the production casing. And so there's enough, so a gas well is because of the drive mechanism at depth. You don't need to pump it. So there's enough gas drive, expansion gas, to drive that reservoir. So they're simpler at the surface, and there's enough pressure then to drive that into a flow line. So what happens is the operators, there's really no economic benefit from them to strip the infrastructure off of sub-economic gas well and try to transfer it over to the gas well that it might think would be economic. So that infrastructure gets left in place, right? When they do that, it keeps a lid on the system. Right? On the oil wells, they just opened it up to the atmosphere. Oil reservoirs now get gas into the atmosphere. On gas wells, because the infrastructure is in place, they keep a lid on the system. But what happens in time, and that video, that last video Deron showed you, where you can see the gas bubbling out, all the valves are closed on that well. There was not one open valve, but when you're a 45-year-old valve, guess what? You start to leak. And so even when you get really small leaks, they come out at high pressure, and there's no way for atmospheric gas to get into that system because the pressure in the reservoir is so much greater than atmospheric gas. So that's the reason why as you burn gas wells can be more, higher concentrations of methane. So sorry, that's a long story short on that. All right, let's see if I can advance this sucker. Yeah, okay, good. So to kind of follow up on this conversation here, so again, let's go back and look at, so on the x-axis, there are emissions rate on the logarithmic scale, right? And then here's the mole percent methane, right? So oil versus gas versus other is things like injection wells and maybe some other things we couldn't identify. So what we see is that for methane emission rates that are about less than 1/10 of a gram per hour, the concentrations of methane tend to be less than moles. And you really probably need to be measuring them at a ppm level. So if we had accurate measurements at a sub 1% level, we actually might see some patterns here, but at this scale, we really can't see it. So it just looks like it's less than moles. At 1/10 of a gram per hour, what you see, and it's not a perfect relationship, you'll see a general tendency both in the oil and gas wells. As the rates go up and the methane concentrations go up as well. So again, circling back to Jim Fung's observation that for wells with higher emission rates, you tend to get greater concentrations of methane. So keep in mind, The methane emission rate is a function of two things. First off, it's the concentration of methane that's emitted. It's also the force at which that methane is being driven away from the wellbore, right? So it looks like those two factors kind of work in tandem out here. Back in here, what happens is that we don't know if this low emission rate due to the fact it's just not being pushed out at a very high rate, or if indeed the methane concentrations are pretty low. So we really want to, one of the things I want to do now that we've got our feet under us in terms of making the measurements as we go forward in this project, I really want to have a closer look at this interaction of the wellbore environment and the atmosphere. And I want to show you an example of that. Next slide. Yeah, so this example comes from Christian County. By the way, this property is for sale. So if you're interested, let me know. I get a finder's fee. So, yeah, so this is a well that Deron and I looked back in August when it was hotter than you can imagine. And it was a well that was drilled in 1955, completed as an oil well. Okay. And the left photo shows the well board's open 8-inch casing, surface casing, goes down to about 200 feet. And then there's an intermediate casing that you can't see. And then Deron has set up a high flow sampler. As you mentioned, we will tarp this over to capture all the gas on the high flow sample. And on this well, we actually measured emissions of about 35.2 grams per hour, which is just a little bit above average for our overall population, and actually a little bit high for oil wells. So we were a bit surprised by that because it actually runs counter to our hypothesis that these open wells tend to be lower emitters. But there's a caveat here, and there's always a caveat. There's a producing well about 150 feet away. We don't know what impact that has on this well. But we saw this as an opportunity to actually kind of look and see what's going on in the depth in the well. So what we did is we, as part of our usual sampling protocol, we got our sample right at the mouth of the well. So that's the surface sample, right? And then we had enough tubing then to drop down to 10 feet and collect another sample 10 feet below the surface into the well. So what you can see here, nitrogen, oxygen, which I'm talking about, and then of course the methane. And it's, again, if we look at nitrogen, oxygen, both for the surface and the foot samples, they're right at atmospheric. So atmospheric gas is the main player contribution to nitrogen here. And what you can see is that actually methane concentrations pick up quite a bit, just over the course of the distance of 10 feet. But there's another factor that we can look at here, just to look at the interactions aside from the nitrogen, oxygen versus the methane. And that's this property of gas that we call gas dryness or wetness. It depends on who you're talking to, but principles are the same. So what we do here is we take the concentrations of ethane, propane, and butane. So that's the C2, C3, C4 fraction as a ratio to the concentration of methane. And so that's, like I said, we call this gas dryness or wetness. And typically, the greater the concentrations, these higher molecular weight hydrocarbons, we call that a wetter gas. The concentration of methane, we call that a drier gas. And so what we see is we go to depth, 10 feet to the surface. That ratio actually decreases. So i.e. the gas becomes drier, okay? And the question becomes is, so if we think about interactions about why that might occur, it could be a simple case of infiltration. In other words, just the greater concentration of nitrogen and oxygen at the surface level versus 10 feet, which makes sense, right? Or it actually could be due to a geochemical reaction in which some of these higher molecular weight hydrocarbons are starting to be oxidized. Okay. So we can actually probably eliminate one of those factors. We can, as being a potential contributor to that shift to this lower ratio. Because what happens when we go from here to here, what happens to the methane concentration? It drops, right? So if the methane concentration is dropping, That means we're not increasing the methane concentration in the denominator. So that shift to a lower value means that we've got to be losing some of these higher molecular weight hydrocarbons, right? And that's likely occurring through a process of oxidation. So it turns out that maybe there's a combination of both infiltration, but also oxidation occurring in the really shallow part of well bore. So we can test that hypothesis further. I actually collected carbon and hydrogen isotopes on these samples. I'm not showing them right now because I'm still sussing them out, trying to understand them. And so, but what I will say is that the carbon and hydrogen isotopes, both the surface and the 10-foot sample on methane, were actually quite similar. Certainly, yeah, they were similar enough that based on the measurement error in the isotope measurements, that I couldn't really distinguish them, right? So not only that, they tended to have a slightly negative value, more negative than I would have expected. They were about either minus 52 or minus 55 per mil. That's getting at the borderline of actually microbial gas. And it turns out that some of these wellbore systems, especially if you have groundwater moving into them, that the organic matter from the hydrocarbons can actually be a food source for methanogens. So it may very well be the case that the methane that we see evolving off of this wellbore is both a combination of thermogenic gas at depth and then some small contribution of microbial gas at a shallower level. Like I said, I'd like to suss that out some more, and so we'll revisit that topic as we go forward. So what I'd like to do is just kind of wrap up here, kind of looking forward to 2 weeks from now, when we'll have Stacy Woods. So Stacy Woods has been working with us on this project. She's been working with me for at least 3 years now, and she's a geospatial consultant. I won't get into the details of how we came to know each other, but she's been really a real pleasure and a real benefit on this project, real pleasure to work with. So Deron talked about the challenges when you have a broad population of wells, and then you measure a smaller subset. How do you project the results of that smaller sample set to the broader population, right? So that comes with the statistical challenges. Well, still another challenge is that if you look at the broad population of orphan wells in Kentucky and indeed throughout the country, so at this point, we have about 14,000 that we know about. Barry would argue that we may have that number again that we don't know about. When I say we don't know about, it means that they probably just have, basically the minimal paper record of their location, but we really don't have any details on it. The question is that with a finite amount of money, despite the fact that we're getting robust funding as a result of the BIL, how do you spend that money in the most efficient fashion going forward, right? And so you can see here, how do you, again, with this finite set of resources, manpower, how do you do that going forward? And provide a guideline so that you actually make decisions on a proactive basis rather than on a reactive basis. And so what we have done with Stacy, we've developed an ArcGIS map tool, and it's a map/tool because indeed it's intended to be a tool, used as a guideline for prioritizing wells for plugging. And Stacy is going to get into the details of that on November 15th. And I will see. Let's see here. I guess you already pulled that up, right, Doug? Or, okay, so this is part of the map that we delivered as part of our BIL obligations to the state. Our initial grant obligations. Sorry. So this map shows. Should not have backed up. I got all ahead of myself, but let's just work through this. So this is all the known abandoned wells in the state. Okay, and so we looked at a variety of factors that might influence the potential hazard that an abandoned well represents. Right. So as you can guess, redder symbol, higher the potential risk. The lighter colors, you can see all those represent wells with lower risk. So let's just, as an interest, let's just go right in here, the Mammoth Cave. So just on the south side of the park, you see there's this huge, large cluster of orphaned oil and gas wells. So this comes from the state. And the interesting thing here, so you can see, let's just hover to one of them. So this is so I'll circle back because I forgot to mention this. So this particular well is a gas well. And from an emission standpoint, we think that if you're interested in abating methane emissions, we think that your time would be better spent focusing on gas wells as opposed to oil wells. So from an emissions hazard perspective, we give it one of the highest hazard potentials, i.e. a critical hazard potential. So we actually have numeric values assigned to those. I won't get into those, that weeds, I'll let Stacy. We also have what's called a decay hazard. So we know that with time, wellbore infrastructure decays. And if you produce brines through that well, like oil wells, then that will cause that wellbore to decay more rapidly. So that's a decay hazard. Environmental hazard, which represents things like Deron mentioned, for that well that was in Breathitt County, which was underwater. So are these wells are in floodplains, or other types of situations where they might represent environmental hazard. And then finally, a public safety hazard. In this case, the proximity to Mammoth Cave National Park would give it a higher hazard ranking. So you can imagine, so this particular coloration scheme represents the aggregate of these four inputs. And each of those four inputs has a variety of other factors that are listed under them. Again, I'll let Stacy get into that. But you can imagine that someone might come along, a policy user, and say, well, I really don't care about methane. So as a matter of fact, I'll give you an example. The National Forest Service and Daniel Boone, when I first started working with them, they could care less about methane. Well, that's not right. Let me put it this way, methane was not a priority. You know why they were worried about abandoned wells? Because people centering their four-wheelers and other things on top of them. So they're worried about them from a recreational hazard standpoint. And so, for example, if you had a national recreation trail running right through the middle of this, then from a public hazard standpoint, it would get really high potential hazard rate. So the cool thing about this is depending on what your focus is and what type of hazard you're interested in, you can then focus on these areas and use that as a guideline going forward. And we see this as a living document as we go forward in this project, as our priorities change and we have other areas of focus as we get more information going forward. But again, I think that this type of thing be the type of tool that the state and potentially outside the state, other municipalities and organizations that are trying to prioritize wells will be able to use. So that's, I think, all I have. And Deron and I are happy to answer questions. Thank you. By the way, we're hiring. Hey, Corbin.
Marty, did you see the relationship between noted that there are some significant emitters rather than each one is not emitting the same amount? Is there any relationship between strata that the well was producing out of relative to the emission numbers?
So that's, get back to Deron's comment about subtypes. That's exactly what that does. It creates the reservoirs into, I'm using the lithostratigraphic unit. Thank you. And the type of hydrocarbon that feeds this. At this point, we don't have enough data with only 119 wells. Those measurements distributed among like 11 subtypes right now. We don't have enough data to make a definitive comment to the question. But that's exactly how we're going. But it turns out that well subtype plays an important role in the decay hazard. Because what happens, we know we have very good control on the variation of salinity, brine salinity for depth. So we know for a fact that across both basins, in south central Kentucky and the southern Cincinnati arc is that the brine salinities increase all the way through the Silurian. So most saline brines are in Silurian age rocks. When you drop into the upper Ordovician, into the Knox, the salinity actually pulls back, and it becomes fresher. So if you have Silurian age reservoirs that are very old, the wellbores are real, there's going to get a really high ranking as opposed to say a Pennsylvania age reservoir, which the brine salinity is so low. We had not anticipated that, but we kind of, as we were working the problem, we thought, oh, well, we can use it this way. But yeah, we've got to get more data before we can make any comments about the particular reservoirs that might tend to be higher.
Mentioned that the nitrogen, when you had your combo on the one axis. Pretty low. Is there a way to make sure that you're not near any nitrogen frac wells? Or that they're not near any low frac wells?
Yeah, so the question is, and this is really, yeah, this could be an issue going forward. So the question is, are we sure that we're not getting a nitrogen input from offset wells that were fracked with nitrogen? So that's a pretty common practice in eastern Kentucky, especially for unconventional reservoirs. So to date, almost all the orphan wells that have been put up have been in conventional fields that historically have been treated either through acidization or nitroglycerin. So they just blew stuff up, right? And but going forward, I fully anticipate that as this expands into the big sandy gas field, that we'll have to keep an eye on that, because that's what we're getting into areas that were, treated with nitrogen foam fracs and things like that.
That temporal sort of instability is interesting. Going into this next phase, is there any merit or idea to do more semi-permanent monitoring on a well, try to get a sense of how that behavior is working over time?
Yeah, we bought some tents. I bought tents for Deron and Madison to spend the night so they can hang out. I'm joking. So, actually, yes. So that's now, like I said, now that we've kind of have our feet under, so we have our techniques down, we're going to start targeting wells, both to look at variations, say over time, monthly or seasonally, but these also over the course of the day. So the one thing we served in the Well Done Foundation data, Deron didn't show this, but if you look at the flow plots over the 24-hour period, there's no question that probably for 70% of the wells, the rates drop off at night. And the question becomes, is that rate drop off due to the fact that this chamber or the flow meter that's setting on the well cools down? Or is this indeed the well bore that's in which the emissions are decreasing? And so the way we're going to get that is we're going to try to get wells that are close enough by that we can get out. If you get out, say, early in the morning at 5 or 6, you're still under quote unquote nighttime conditions, right? Do a measurement on the well. So the great thing about high flow sampler is that we don't have to enclose the well. We can measure it and then come back maybe later in the morning and again in the afternoon to see if we can see variation. But yeah, there's no question that that's a thing that we need to address. I expect that we're going to see that variation on low emitting wells as opposed to high emitting wells. And that's important because almost all the data that are reported so far on a national basis, just when they were measured in the daytime, right? So it could be that the data sets that EPA is using for their emissions factor may be skewed a little bit to the high end because all the measurements are taking place in the daytime. Is your phone?
So the slide on the prison very well, so the different concentrations of methane and so this fascinating. To describe possibility of expansion across the difference in dryness.
Right.
The problem with that just because the methane is wider, more waterable,
There you go. I'm thinking like a geochemist. I like that. So, Jim Fung's observation, and he's right about this, is that if you kind of look at diffusion coefficients for these different gases, right? Methane's lighter, so therefore it should be diffusing at a faster rate. So, and indeed, that may come back to the fact that we don't when we look at the carbon isotopes on the methane, if we don't see that it's reacted, right? It may indicate that, you know, maybe it is diffusing off faster compared to the ethane, propane, and butane. We know that the reaction kinetics for those heavier gases are, they react more quickly as opposed to methane. But no, that's an interplay that it probably do some sampling and maybe do some, from a geochemistry standpoint, we would do some modeling in which we just kind of look at diffusion coefficients and see what that looks like, what that gives us, right, an in-member model. Then do an in-member model where we just react those gases and see what we observe and measure fits with those two, see if it provides any insights.
So, isotope composition.
Yeah, it'd be fun to do the isotopes on the ethane, propane, and butane, but you gotta have pretty deep pockets. It's very expensive to do those. But it might be worthwhile doing on a few select wells.
And private property.
Huh?
Spending private property, which is to a field experiment.
Sure. Okay, thanks, everyone. Appreciate your Friday afternoon.